And I'd like to thank the organizers and Mike for this opportunity to speak. I'll be talking to you about joint work with Dennis. Oh, lights. That's okay. Yeah, thank you for the reminder. And I'm going to talk about a problem that originates in the algebraic topology of compact Hermitian symmetric spaces and a differential geometric approach to this. So no conformal geometry, but a lot of representation theory. And it's really a treat for me to be able to give this talk to an audience full of people who know representation theory. I can throw a little bit more at you, and also I have a question about a phenomenon we've observed that we don't quite understand. So if you have something to say, we would love to talk to you. All right, so I'm going to break the talk into three pieces. The first is the motivating question, which is due to Borel and Haflinger. We'll look at some knot definitions, and I'll give some examples so you have an object to hold in your hand as we go through the talk, and we'll go through the motivating question. Oops. So I'm going to write my compact Hermitian symmetric space as X, and you should think of it as G mod P, and go ahead and think about the irreducible CHSS so that G will be a simple complex Lie group and P is a maximal parabolic. Your favorite example might be projective space. Topologically, that is too easy. We pretend to understand the topology of CPN. So if you want another example to hold in your hand when you think about a compact Hermitian symmetric space, the next best is the Grassmannian, the space of k-dimensional subspaces in complex dimensional M space. And the classical irreducible compact Hermitian symmetric spaces are the Grassmannians, the hyperquadrics, which we won't talk about too much because they're also not very interesting topologically, the Lagrangian Grassmannians, and the spinor varieties. And there are two exceptional cases that come from E6 and E7. These are the Cayley plane and the Freudenthal variety. Okay. So you can visualize these or think of these spaces as algebraic varieties. You pick an irreducible G representation. So you're thinking of your compact Hermitian symmetric space as sitting inside the general linear group of some complex vector space. And if G acts irreducibly, so it doesn't preserve a proper subspace, then there is a unique compact orbit in the projectivized vector space. In projective space, that unique compact orbit is the orbit of a highest weight vector or a highest weight line, and P is the stabilizer of that line, that point in projective space. This is a smooth homogeneous variety, so it's a very nice space to look at. And up to this point, I have just described to you some homogeneous varieties. What you get out of this construction will be compact Hermitian symmetric space. We're not actually going to put the Hermitian symmetric metric on the space, but you could do so only if the isotropy action of P on the tangent space is irreducible. Okay, or it's one-graded, if maybe you've seen that language, having read Chapin Slovak. The Lie algebra, G, is one-graded by the parabolic P. Okay? Now, sitting inside this smooth projective variety are some distinguished subvarieties, the Schubert varieties. I'm not going to define them for you, but I will tell you why they're important and give you some examples to think about. And they're important because their homology classes, the Schubert classes, generate the integral homology for these varieties.
What part of that? Did you see the constant? The integral? Or
So I think the integral structure, in the general case, it was certainly known beforehand for the Grassmannian, but I think this dates to the double paper that you, I guess the second version from the Bott-Borel-Vey. Yeah, the one on Schubert cycles. Okay, so here's an example of one Schubert variety sitting inside the Grassmannian. You fix a subspace W of this codimension k plus L minus 1, and then you look at all the k-dimensional subspaces of complex space that have a non-trivial intersection, This is a non-generic condition. Just by dimension count, you'll usually expect this intersection to be trivial. So this gives you a proper subvariety. It has codimension L inside the Hermitian symmetric space. And what I wanted to emphasize here is that it's an example of a singular variety. It's not a smooth subvariety of the Hermitian symmetric space. And in fact, most Schubert varieties are singular, and you can argue that they are in fact the most singular varieties, complex varieties representing that homology class. It's a non-trivial statement, though, I think, using some of the known facts about the Schubert varieties and a deep result of Hironaka. Okay. So given that most of these representing varieties for the Schubert class are singular, you might ask, when can we find a variety, not necessarily just a complex manifold or a real submanifold that is smooth and represents the homology class? When can we find a smooth, complex subvariety that represents the homology class? And this was a question posed by Borel and Haflinger in 1961. When that smooth variety Y exists, I'm going to say that the Schubert class is smoothable. The language is a little bit inconsistent in the literature. So that's what smoothable means today for this 40 minutes that remain. Okay. Now, in those examples I gave you before, if you fix x to be 1, then you get a Schubert variety of codimension 1 sitting inside the Grassmannian. And this object is obtained by taking the intersection of the Grassmannian in the ambient projective space with a hyperplane. Okay. It's singular in this case, but generically, due to Bertini's theorem, you can just jiggle that hyperplane a little bit and you'll get a smooth intersection. That smooth intersection will be a smooth variety representing the homology class for x sub 1. Oh, and let me just mention as an aside, why am I using the w's for the Schubert varieties, this x sub w notation? This is just an indexing set for the Schubert varieties. If you like, the w are elements of the Hasse diagram associated to the parabolic. And if you just want to think about the Grassmannian case, they're the partitions that define Schubert varieties in that case. Okay. So Hartshorne, Rees, and Thomas looked at this problem, and they showed that in spite of the fact that we can smooth the hypersurface Schubert variety, there are examples of Schubert varieties that can not be smoothed in any reasonable sense, even if you step outside of the category of a smooth subvariety and just allow yourself a real oriented submanifold. X sub 2 in the Grassmannian of 3 planes and 6 space cannot be smoothed by, well, is that there? Wrong place. Okay. If we drop down and look at 2 planes and 5 space, then the corresponding Schubert variety we can write as the difference of 2 smooth subvarieties, but it cannot itself be smoothed. Okay. So that's the motivating question. I want to tell you a little bit about what is known so far for this problem, and I'm going to start backwards historically. I'll start with Izet Koskin. His results are quite recent, but they're geometric and they're algebraic geometric in approach. And then I'll talk about the differential geometric approach that I'm going to go over today and some of the early results using that system. Okay. So first, Koskin gives what he calls a nearly sharp, and it's very close to complete description of the smoothable Schubert classes in the Grassmannian. So modulo some subtle questions about inclusions of one Grassmannian into another, that's what nearly sharp means in this case, the question of Borel and Haflinger is just about understood for the Grassmannian for that case. So if you want to hold a different example in your hand, you could bounce up to the Lagrangian Grassmannian to think about. There's a related question to the smoothability question, which is whether or not a Schubert class is rigid. So are there any other varieties, singular or smooth, that represent that Schubert class? And if the answer is no, if the only irreducible insert an irreducible here. If the only irreducible varieties homologous to the Schubert variety are just G translates, then we say that this class is rigid. So for example, if the class is rigid and the variety is singular, the class is certainly not smoothable. But it's also an interesting question. What other sorts of distinguished representatives can we have for this homology class? Okay, and in this category, if we're talking about this topological question, a representative by a algebraic variety would be something distinguished. Okay, you could think a little bit about this like finding a harmonic representative for cohomology on a Riemannian manifold. Okay, what's a nice representative of this homology or cohomology class? Okay, and even better than the first theorem, Koskin identified all the rigid Schubert classes inside the Grassmannian. Okay, he can hand you a complete list. There's still some work to be done here. It's not clear in the flexible cases what are the varieties Y that you can pick up representing the flexible classes. So there's still some, oops. Okay. So now I'll talk to you a little bit about this differential geometric approach. This is really remarkable, right? That we have this algebraic topological question that we can approach using differential geometry, have a system of PDEs that will help us answer this question. It's very cool. So Maria Walters, in her 1987 PhD thesis, looked at the problem on the Grassmannian, and she proved this theorem in that setting, and Bryant proved it in 2001 in the general setting. And if you open up the collection of varieties you're willing to look not just for varieties Y that are homologous to X, but that are homologous to a multiple of X, then those varieties are characterized by a differential system. Okay? I'll describe that system later. The takeaway message here is just that we can use PDEs to look for these varieties. Okay. So one more definition for rigidity. We'll say that the variety itself is sure rigid if the only solutions, the only irreducible integral varieties for the sure system are Schubert varieties, or their G translates. And since we're in homogeneous space, a G translate is the same thing as a Schubert variety to us. We're not going to be fussy. Okay, and if it's not rigid, we'll call it flexible. And so let me just emphasize how this gets back to the original motivating question. If you have a Schubert variety that is rigid, then the Schubert class is certainly rigid. You would just take R equal to 1 in the equation 1 above. So in particular, if the Schubert variety is singular and sure rigid, then it's not smoothable. Okay. So as I mentioned, this is really, really remarkable. The sure system, which characterizes these varieties Y, whose homology is an integral multiple of the Schubert variety, can only be defined and give you this characterization for the compact Hermitian symmetric space. And it really does depend on the fact that if you look at the nilpotent complement to the parabolic algebra in the Lie algebra G, that this is abelian. Another description for the compact Hermitian symmetric case. All right, now some of these Schubert varieties are going to be flexible for trivial topological reasons, and we won't worry about them. We'll just shuttle them off to the side. And this trivial topological reason is that sometimes the homology in real dimension 2K will be generated by a single Schubert variety. And if it's generated by a single Schubert variety, then any variety of dimension K will have homology equal to a multiple of that Schubert variety. So the variety X sub W is certainly sure flexible. As an example, the following are sure flexible. I mentioned that we would not be very interested in projective space. Every Schubert variety is sure flexible. Every proper variety is sure flexible. We wouldn't call the ambient space Pn or a point flexible. And for this reason, if your compact Hermitian symmetric space contains a linear subspace and your Schubert variety sits inside it but is not equal to it, then that Schubert variety will also be flexible. Oops. Okay. And I think I also mentioned that the hyperquadric Q, those compact Hermitian symmetric spaces, are topologically not very interesting. The odd dimensional quadrics have this condition, h sub 2k is equal to z for all k. And for the even dimensional quadrics, it fails only in the middle dimension. And then in that middle dimension, there are two Schubert varieties, so giving you integral homology z2. And in that case, the generating Schubert varieties are both maximal linear subspaces. Okay. They turn out to be rigid. All right, so I'm going to describe some of the results of Walters and Bryant now using this Schur differential system. Maria Walters looked at the smooth Schubert varieties in general and some of the low codimension Schubert varieties in the Grassmannian of two planes in m-dimensional projective space. And Bryant generalized this quite a bit, looking at the smooth Schubert varieties in the Grassmannian, the Lagrangian Grassmannian, the maximal linear subspaces in all of the classical compact Hermitian symmetric spaces, and singular Schubert varieties of low dimension and codimension. The arguments here use a lot of representation theory. They use the PDE as an exterior differential system. But they're very ad hoc. They're very case by case. The next step forward in this problem was by Jaehong Hong, who developed a beautiful uniform approach to this problem for the for the smooth Schubert varieties. So this is really looking at the Schur rigidity question. When does there exist another variety whose homology class is an integral multiple of the Schubert variety? Okay. And with exceptions that are ruled out for those trivial topological reasons I mentioned before, she showed that all of the smooth Schubert varieties are Schur rigid in the compact Hermitian symmetric spaces. And the as I mentioned, the omissions are for topological reasons. This is a really, really beautiful argument. I want to say a little bit something about it now because it's lovely, and because I want to talk later about why it fails for the singular Schubert varieties. So when you set up the system to study these varieties, and you start to push it through the EDS machinery, a Lie algebra cohomology appears. This Lie algebra cohomology satisfies the hypotheses for that beautiful theorem of Costant, and that reduces the calculation of that cohomology to Weil group combinatorics. And this is significant because if you can show that part of that Lie algebra cohomology vanishes, then you've shown that there are first-order obstructions to flexibility. And so you take this problem that's initially calculus, because we have an EDS, and you reduce it to linear algebra, the Lie algebra cohomology, which is still kind of hard. And then all of a sudden you're just down to Weil group combinatorics and this beautiful result of constants that's so well understood. Okay. The publication dates are out of whack, but after she had this smooth result, she used the foliation structure of the singular Schubert varieties to identify a large class, almost all of them, of the singular Schubert varieties in the Grassmannian for which there exist first-order obstructions to flexibility. And depending, if you read her paper carefully, you see that she pretty much gets everything, but it's not stated, not everything on the list of for which there exist first-order obstructions. So I only have to look at first derivatives of the system to identify an obstruction to flexibility, but it will also be a first Lie algebra cohomology group. That's yeah. So like torsion. Should be thinking torsion. Okay. So that's where we are, and I'm going to tell you a little bit about the main result that we have on the Schur system. We'll go over some examples. I'm going to give you a little bit of a vague statement of the theorem just so you know what it's about, and then as we go through the talk, I'll be a little more precise. Okay. So we've generalized Hong's work and have now a complete list of the Schubert varieties in any compact Hermitian symmetric space for which there exist first-order obstructions to flexibility. Okay. This includes, well, all of the Schubert varieties for which there are first-order obstructions to finding that smooth variety that Borel and Haflinger were initially after. It recovers, oh yeah, this is actually very cute. We cannot prove beforehand that if there exist first-order obstructions to flexibility for a Schubert variety, then the same is true of the Poincare dual. But a posteriori, looking at our list, it's evident, which is interesting because in general it's not expected that if a Schubert class is rigid, then its Poincare dual will be as well. This recovers the results of Walters, Bryant, and Hong. And I just want to point out that this is not necessarily a complete list of the sure rigid varieties. It's really only those for which we have first-order obstructions to flexibility. There could be higher-order obstructions. And those examples of Hartshorne, Rees, and Thomas that I dangled at the start of the talk are not on the list. Okay, so I want to show you what the main theorem looks like pictorially, and we have Hasse diagrams for that. So we're looking at the case of a Lagrangian Grassmannian C5 mod P5. So that's the maximal parabolic associated to the fifth root, and this is a 15-dimensional smooth variety. And what is in front of you is the Hasse diagram associated to that variety. Each point is a Schubert variety, and there's a line joining them if one Schubert variety is contained in the other. Okay. All right, so some of them we're just going to throw out for the trivial topological reasons. This, for example, this is the zero-dimensional Schubert variety of point. This is the one-dimensional Schubert variety, and so on, two-dimensional, three-dimensional, three complex dimensional. So this is sitting inside H sub 2. It's the only generator for that homology. So we have flexibility for trivial topological reasons. Okay, and now circled in red are those for which there exist first-order obstructions to flexibility. So those are the Schubert varieties that show up on our list. And I'm going to decorate the Hasse diagram with some integers that I will explain more carefully later. What I want to point out now is just that the smooth Schubert varieties inside this list are the ones where the integer a is equal to 0. So those are the cases that Hong or Walters and Bryant would have already studied for the singular setting. And you'll notice some symmetry in this diagram. That's the Poincare duality statement pictorially. Now, what's kind of wild is, oops, okay. So what's kind of wild is now let's switch to the spinor variety, D6 mod P6. That's also a 15-dimensional variety. And if you compare, I might have to use the pictures. If you compare the two pictures, they have the same Hasse diagram. And this is the representation theory phenomenon I was alluding to that we don't quite understand and would like to understand better. Why do these two varieties have the same Hasse diagram? It seems to be true in general that Cn mod Pn has a Hasse diagram of Dn plus 1 mod Pn plus 1. The integers change, you will notice, but the sure rigid varieties do not change between the two, which is kind of funky. That is preserved. Okay. And then one more example for fun. That's the E6, P6 example. Lots of varieties thrown out for trivial topological reasons in that case. Okay, I'm going to describe a little bit more Hong's approach for the smooth Schubert varieties because I wish to talk about the obstructions that arise in the singular case and how Dennis and I got around those. So there are two key tools that go into her proof, and the first is a beautiful, well-known description of the smooth Schubert varieties by connected subdiagrams of the Dinkin diagram. And this is the hieroglyphics that Mike talked about in some of his talks. You can pack an enormous amount of geometry into some lines and dots. And one of those geometric data you can pack in are information on the smooth Schubert varieties. And it's basically the statement that for the compact Hermitian symmetric spaces, the smooth Schubert varieties are homogeneous themselves. That's not true for arbitrary G mod P. And then, as I mentioned, there's a Lie algebra cohomology that arises in the analysis of the Schur system. And first order obstructions to flexibility is equivalent to the vanishing of a subspace of that cohomology. And the theorem of Costant reduces the calculation for the cohomology to Weil group combinatorics. Okay. So the first obstruction to generalizing to the singular case is that there's no analogous description of the singular Schubert varieties in terms of these hieroglyphics. And the second is that Costant's theorem does not apply. You're just out of luck. Okay. So let me describe to you now how we got over those obstructions. First, we have a description of the Schubert varieties that generalizes the description for the smooth Schubert varieties. It's given by an integer and a marking j of the Hasse diagram. And that integer is 0 precisely when you have a smooth Schubert variety, and this description can be seen as a generalization of the characterization by connected subdiagrams. Or if you're very familiar with the partition description of the varieties in the case of the Grassmannian, it's also a generalization of that. There's a recipe to go back and forth between the partition dictionary and the AJ dictionary for the Schubert varieties. Okay. And the second, so this is a nice solution. The second solution is a little less satisfactory because we don't have so beautiful a result as Costant does in his description of Lie algebra cohomology. But the approach that Costant takes to prove his result does work here. If you remember what he does, he defines an algebraic Laplacian and shows that as a module for an appropriate group, the kernel of that Laplacian can be identified with the Lie algebra cohomology. He then analyzes the spectrum of that Laplacian, and that's where his Weil group combinatorial formula comes from. So we follow his approach to find the algebraic Laplacian, again with this property, and that's enough for us to be able to get good representation theoretic information on the Lie algebra cohomology. Okay. So I'll be more precise about this theorem in a moment when I talk about an example with the symplectic Lagrangian. But as I mentioned, we have a complete characterization of the Schubert varieties by that integer a and a marking j sub w. And I want to show you what it would look like in one particular case. So here's the Dinkin diagram for C8. That's the Lie group preserving a symplectic form on C16, 16-dimensional complex space. And to indicate my choice of homogeneous variety or my choice of parabolic, I just mark the 8th node, the last node. And everybody that's left unmarked, I can recruit for my submarking j. So in this example, in orange, that's the 2nd, 5th, and 6th nodes. And so we'll just call j 2, 5, and 6. That's the marking of the subdiagram. Okay. Once you have this marking, there's some representation theory in here. It gives you a distinguished element of the Lie algebra of the parabolic group P. And there is an eigenspace decomposition of the tangent space to the homogeneous variety into to eigenspaces for EW. So for example, EW will act on this component by -1, on this component by -a. And then if you take a subset of this decomposition working backwards down to 0, what you get is necessarily a tangent space for some Schubert variety. And once you know what the tangent space for that Schubert variety is, you know what it is. That's sufficient information to determine what's going on.
So any A between 0 and big A?
Yep.
Works?
Yeah. So this is not the sharp description. It's for some W. Right now I haven't given you a bijection. I'll give you a bijection on the next page. Oh, and I am tacitly restricting myself to proper subvarieties. If you take, so I would not, for example, take big A, which would give me the entire Hermitian symmetric space. Okay, so an example of what the precise statements for our results look like in the case of the Lagrangian Grassmannian are the following. So first, to characterize the Schubert varieties, you can take any subset of those nodes that are left over once you mark the last node. Any subset at all is fine, but it does put constraints on your choice of the integer A. It's going to be either, oh, this is an old file. It's going to be either the number of elements in the marking J or one less than the number of elements in the marking of J. But modulo that restraint, there's now a bijection between those J and A and the Schubert subvarieties. Then, in terms of this description of the Schubert subvarieties, you can describe all of those for which there exist first-order obstructions to flexibility. And in the case that your integer A is exactly the number of elements in the submarking, what you need is for those marked nodes to be distributed so they're not adjacent to each other. You need a little room. Okay. And similarly, for the case that A is one less than the number of elements, here we are allowed to double up at the very start of the marking, but this statement here says that we can't stand right next to the nth node, the last node on the Deacon diagram. We need a little space before we start marking. Okay. Oof. And, right. So just so you haven't forgotten the original question, which was smoothability, these guys are not smoothable. They're first-order obstructions to their being smoothable. The Schubert classes, homology classes. Okay, so I have some time left to tell you about the proofs and what goes into these statements. So let me introduce you to the star, which is the Schur differential system. I'm going to use some simplifying notation. I'll use little n for the tangent space at the origin for the compact Hermitian symmetric space, and sub w for the tangent space of the Schubert variety, and this norm of w is just the dimension of the Schubert variety that we're looking at. A beautiful theorem of Constant gives a p-module decomposition of the kth exterior power of n into inequivalent irreducible modules. And even better, he showed that the characterizing highest weight line of those irreducible modules is precisely the tangent space to a Schubert variety of dimension k, since we're looking at the kth exterior power. Okay? So now we're going to think of this Grassmannian of k-dimensional subspaces that are tangent at the origin as sitting inside a projectivized vector space. So I can slice it with the projectivizations of these linear subspaces, the I sub w. And that slicing of the Grassmannian is what gives you the Schur system at a point. So these are the set of admissible tangent planes under the identification with the Plucker bedding, the admissible tangent planes at the origin for my solutions to the Schur differential system. And to get the rest of the system on the entire, whoops, oh, he's important. I'm going to come back to this guy in a moment. He's important. Okay. To get the rest of the Schur system on the entire compact Hermitian symmetric space, we just take those allowable tangent planes at the origin and push them around using the group action. Okay. All right, so I mentioned above that n sub w is a highest weight line inside this module. So in particular, we could look at its orbit under the action of p, and it will at least be contained in the slice, but it may not be the whole slice. And whether or not it's contained in the slice is going to impact whether or not we have flexibility. So I'll come back to that containment in a moment. Okay, and again, the integral varieties are those for whom the tangent space, y sub naught, are the smooth points, where I can talk about a tangent space in a way that makes me comfortable as a differential geometer, are contained in the this subbundle of the Grassmannian, this R sub w that we've picked out to define the Schur system. Okay. All right, so the analysis goes as follows. It's basically a moving frames approach with exterior differential systems. We take this Schur system, R sub w, and we can lift it up so that it, oops, wrong one. We can lift it up so that it sits in this submanifold of the general linear group. And the script G you should think of as our representation of G. It's G's, the Lie group G's embedding into the general linear group for this representation we started with. P of V is where our projective variety is sitting, our compact Hermitian symmetric space. Okay? And as you churn through the EDS machinery to study this system, a Lie algebra cohomology pops up, and it admits a E sub w graded decomposition. That E sub w, remember, is the grading element, that element of the parabolic subalgebra that is given to us by our choice of marking J on the subdiagram. I'm sorry, what I wrote on the board is not accurate. That decomposition just comes from the original parabolic P that defines the Schubert variety. I cheated a little bit. Sorry about that. It's a similarly constructing grading element, but that's not the right one. Okay. So first, remember that I mentioned that we have this highest weight line whose orbit sits inside the system as it's located at the identity. And when containment fails, the system is flexible. It's just, if you're looking for rigidity, you must have equality. Strict containment will not get you anywhere. And it's this first graded component of the Lie algebra cohomology that plays a role in determining when you have equality. So that's where that component comes in. Then the positively graded component of the Lie algebra cohomology over here, it's behind me. Once you have this necessary equality, the positively graded component comes into determining where there are first order obstructions to flexibility. Now, if the entire cohomology vanishes, then you do get first order obstructions. It's not if and only if. You really only need a subspace to vanish, but I'm not going to write down what that subspace is. Okay. Let's see. Yes, but that won't happen. This is always non-zero. But if this vanishes, then I get rigidity, if the positively graded component vanishes. So let me say a little something about how we compute this Lie algebra cohomology to get to those two yellow boxes. Okay. So again, as I mentioned, the step one is to construct an algebraic Laplacian with the property that the kernel of this Laplacian, what you'd think of as being the analogs of harmonic forms on a Riemannian manifold, is naturally identified as a module with the Lie algebra cohomology that we're interested in. This is, by now, a straightforward construction. It just follows a Costant's approach. Okay. And so now that we have this, this kernel, we wish to look at the positively graded component to determine the first order obstructions to flexibility. I'm going to walk backwards from what I described in the previous slide. We're going to start with the positively graded component. And so you plug into this analysis two tools. The first of which is representation theory, and that AJ characterization that I mentioned, and then the EDS machinery. This is really pretty. This is really pretty because you start to work with the exterior differential system and you hit torsion, which the torsion is basically the numerator of the Lie algebra cohomology. The representation theory gives you information about this Lie algebra cohomology. You get rid of this torsion, and then you have a sort of a bit of a graded prolongation, not a full prolongation in the usual sense, but a graded prolongation. So the torsion of the EDS is feeding back into the representation theoretic data, and they just kind of braid in and out with each other. It's really pretty.
So what do you mean by torsion?
I mean torsion when you look at the tableau. Well, no, when you look at the linear Pfaffian. The Schur system lists to a linear Pfaffian. You differentiate, you need to kill off torsion. So the Lie algebra cohomology, as you will want to think about it, the numerator is torsion and the denominator are the admissible normalization to kill off freedoms of coefficient. Okay. And then step 3 is to determine when that necessary equality holds. And remember, we look at the 0th graded component of the kernel in order to go through that analysis. We don't have the EDS and the helpful information from torsion backing up at this point. What we do have is a filtered complex, and so we need to whack it with a spectral sequence. But I'm really thrilled that I got to this page for the following reason. I think in Mike's second talk, he really tried to impress upon people in the audience that if you want to do geometry in the sense of this conference, you've got to know representation theory. You need to be able to interpret things like Dinkin diagrams and all of that beautiful data and structure that you give us, that it gives us. Mike gave a really nice collection of informal talks on spectral sequences in Brno in August. And I don't know if this is actually what he said, but what I remember him saying is that you've got to learn spectral sequences or you will be a fool to yourself and a burden to others. And so if there are any young, impressionable graduate students in the audience, I think that holds for spectral sequences and representation theory. So it's a very motivational statement. and I will stop there. Thank you. It's time to wake up, Ian. I try not to think about who Mike was making eye contact with when he said that. Yeah. Thank you.
Well, I was just going to ask about the other bits of the pasta diagram where you've got you have some nodes which have red bits on because you've got first order abstractions. What about all these other nodes?
That is ongoing work. There's quite a bit more that's interesting to be done. So there are, first of all, 2 courses of action. If you really want to study the Schur system, we need to prolong it and see if there are higher order obstructions. When there aren't obstructions, when the system is flexible, what are the integral varieties? That's very interesting. That'll be difficult in a long ongoing project. On the other hand, you have this really beautiful result of Koskin's using algebraic geometric methods, which he claims are not that sophisticated but are underused by the community in general. He's able to push this forward using the partition description of Schubert varieties. We are wondering if this AJ generalization, which you should think of as generalizing the partition description to other compact Hermitian symmetric spaces, can be used to obtain those very nice results for compact Hermitian symmetric spaces in general. So, yeah, we don't know, but we're working on it.